Okay, let's continue our discussion on the differential linear momentum balance. A few classes back we had introduction to tensor, and we said tensor represents a physical quantity which require to be represented using a magnitude in two directions. And then we saw the stress tensor as an example for a tensor, okay, because 9 components were there, 9 pairs of directions were there. Objective of this next few slides is that we are going to discuss one more tensor which also appears in the linear momentum balance equation. Okay, that is the objective of the next few slides. So, just to recall, this slide is a recall slide, same as what we discussed earlier. Tensor represents physical variables which have a magnitude and two directions. Vectors are for physical variables with a magnitude and one direction. Now, we represent tensor in terms of its components form using this equation, and there are 9 components in a tensor, and each component is associated with a pair of directions, and that is what these diagrams tell you. For example, tau xx associated with I and I pair of unit vectors, and then let us say if you take ij the component associated with the unit vectors I and j is tau xy. Similarly, other pairs of directions. And we also discussed that the components change with coordinate system. Tensor as such does not change with coordinate system. We also have that sum of diagonal elements is independent of coordinate system. Okay, that is a review of tensors. So, now the two tensors which I am going to discuss are the viscous stress tensor, which is kind of known to us. The new tensor which I am going to discuss is the convective momentum flux tensor. Okay, so, let us write down the 3 linear momentum balance equations, only then we can discuss the two tensors. So, we written down the linear momentum balance along x direction, y direction, z direction. From this we will identify the two tensors. Right hand side, let us start with something known to us. Right hand side we have the viscous. Earlier we have discussed this as stress tensor for solids. Now we are discussing this as viscous stress tensor for fluids. Now this components of the stress tensor are known to you. Let us look at the stress tensor and the right hand side. Now we know that one row in a tensor represents the components of stress vector acting on a particular face. So, the first row represents the components of stress vector acting on the x face. Now, if you look, that is the way you represent each row. If you understand the column, they represent the components of 3 different stress vectors, and all the components are acting along x direction. Okay. So, if you look at column wise, they represent the components of 3 different stress vectors. Why is it 3 different stress vectors? Because the plane on which they are acting is different, which is represented by the first subscript, but all the forces are acting along the x direction. That is why here you have x, here you have x, and here also you have x. Now we know that in a momentum balance, the right hand side should represent forces along one direction. That is why this 3 set of viscous stress tensor components are appearing in the first equation, meaning the equation in the x direction, and these 3 stress tensor components are appearing in the y momentum balance equation, and these 3 are appearing in the z momentum balance equation. Okay. So, let me repeat, the significance of each row is that they are components of stress vector acting on a particular plane, but what we need is components of 3 different stress vectors acting on 3 different planes, but all the components should be directed along x axis. They are all appearing in the first column, and that is why these the stress tensor components appearing in the first column are appearing in the x direction momentum balance, similarly y direction, similarly z direction. So, understand that if you look at the first row, the first subscript is same because of phase is same, the plane is same. Second subscript is different because the directions are different, normal stresses and shear stresses x, y, z. If you look at column wise, the second subscript is same because they are all representing forces acting along x direction. First component is different because they represent components of stress vectors acting on 3 different phases. Okay. So, now kind of familiar, this is familiar to us, we have done little discuss little more than what you already know. Okay. Now, let us look at another tensor, that is called convective momentum flux tensor, which is on the left hand side of these set of differential equations. Now, suppose if we are writing that stress tensor from these equations, what is that we would have done? We would have taken these 3 components and written as column wise as a first column, then take these 3 components and write as the second column, and then take these 3 and we would have written that as the third column. What we will do similarly, go to the left hand side and write all these 3 components including rho as one column, rho Vxx, rho Vy Vx and rho Vz Vx, and then take these 3 terms, not the derivatives of course, and then include them as the second column. Similarly, here include these 3 terms as the third column, and this is the convective momentum flux tensor formally represented as rho V vector V vector. Okay. We are having 2 vectors side by side, formally it is called the dyad. So, that forms a convective momentum flux tensor. Okay. We will not discuss dyad more formally here, but what we will discuss is the physical significance of these 9 components of the convective momentum flux tensor. But first question is why convective? That is very clear, all these terms are coming from the convective components on the left hand side of the linear momentum balance. So, that is very clear. Why is it momentum flux? Next question, what I have written here is a general expression, all of them are rho into velocity into velocity. Okay. Of course, different directions are there. So, rho into velocity into velocity. Now, we will take the first velocity, understand the first velocity, and that becomes the volumetric flux. We have seen that velocity can be interpreted as volumetric flux, multiply by density you get the mass flux. Okay. And that is what is written here. Now, mass flux into the second velocity, what is that? Momentum flux. You know, mass into velocity is momentum, mass flux into velocity gives you momentum flux along the direction of the second velocity, though I have not written here. So, I will repeat it, each term is rho into velocity into velocity. The first velocity will interpret as volumetric flux. Why do you interpret the first velocity? Remember, rho into Vx is associated with the mass flow in a particular direction, that is why I interpret the first velocity as volumetric flux, not the second velocity. Okay. And of course, multiply by the rho with the first velocity, meaning volumetric flux gives you mass flux, multiply by the second velocity gives you momentum flux along the second velocity direction. Now, next, why is it a tensor? Obviously, we can see that there are, each term is associated with a pair of directions. We have Vx Vx, Vx Vy, Vx Vz, okay, and that is what we will discuss in the next slide. We know that this stress tensor is a tensor because it has 2 directions. We will compare these 2 tensors in the next slide and will also understand why this matrix is a tensor. Okay. Okay. Viscous stress tensor, as we have written earlier, is represented by these 9 components. Okay. Same as what it done in the seen in the previous slide, and then the convective momentum flux tensor is given by these 9 components. Okay. We will just compare these 2 tensors now. We will also understand then why this matrix represents convective momentum flux tensor. Okay. how do you interpret, for example, I am going to take tau yx, I am going to take rho vy vx for case of illustration. The stress element is shown here. How do we interpret tau x? Because it is positive, it is viscous stress acting along x axis, second subscript tells the direction. So, acting along x axis on a positive y plane. Okay. If you look at this diagram, this is the of course positive y plane. So, we should consider the positive y plane here and force acting along positive x axis. So, tau yx represent the component of course of stress vector acting on the y plane, positive y plane, force is acting along the positive x axis. Now, let us interpret this rho vy vx, then you will immediately understand why we have momentum flux tensor. Rho vy vx, to understand that we will use this control volume, we have rho vy vx here, rho vy vx here, and those two terms are written here. And what does rho vy vx delta z delta x represents? To recall back, we said we will represent this as volumetric flux, that just like we had done in the previous slide. With this you get mass flux, multiply this with the area, you get the mass flow rate, multiply by velocity vx, you get the momentum in the x direction. Similarly, of course, this represents whatever is leaving, this represents whatever is entering, but what is it we should take forward is that we are having a velocity in the y direction and that is a volumetric flux, and multiply by rho gives mass flux, multiply by area gives mass flow rate, into velocity gives you momentum in the x direction. So, rho vy vx represents convective flux of x, we have seen why it is a flux of x momentum because second velocity is vx across y plane. Why is it across y plane? The mass flow associated with that is in the y direction. So, there is flow in the y direction, but momentum is in the x direction. That is why I can't just like that give one direction and represent or discuss momentum flux. I should say what is the direction of the momentum, I should say what is the direction of the mass flow which is carrying that x momentum. Moment I say convective flux of x momentum, I should include two directions, direction of the momentum which is x in this case, and the direction of the mass flow which is carrying that momentum in this case which is the y direction. So, two directions are associated to explain each component of the momentum flux tensor, and that is why it is a tensor. In this case the two directions are, one is the direction of the force, direction of the force, and other is the direction of the plane. Here also the first subscript represents the direction of the plane. Why is direction of the plane? Because there is a flow along that direction. Second subscript represents the direction of the momentum. So, both the tensors have two directions. First represents the direction of the plane in both the cases. Second one represents the direction of the force in one case, second case represents the direction of the momentum. Okay. That is why we have we call them as the tensors, one as viscous stress tensor, other is momentum flux tensor. Okay. So, these are shown in a more little magnified scale, not new much new concepts here. The viscous stress tensor is shown more magnified way as a 3D stress element. Okay. This slide of course emphasizes on the direction. We said the two directions are there, direction of the normal to the plane and then direction of the components of the stress vector or the direction of the force. So, three directions are possible, three directions for normal, three directions are force, gives you 9 components of the viscous stress tensor written as a tensor here or a matrix. Okay. Now, if you look at the convective momentum flux, in the previous case we had direction of normal to the plane, here also we have direction of normal to the plane, but for physical understanding I have written as direction of fluid flow, direction of fluid flow, direction of normal to plane, both are same. What is the other direction? Direction of the momentum which is determined by the second velocity. Okay. So, direction of fluid flow can have 3 directions, direction of momentum can have 3 directions, and that is why you have 9 components of the convective momentum flux tensor. Okay. So, this clearly explains how there are 2 tensors, one on the right hand side representing the viscous stresses, one on the left hand side representing the convective momentum flux. Okay. And that is why when we discussed earlier, we are specific about the what is the velocity that should come second, what is the velocity that should come first. When we wrote the rate of momentum entering and leaving, we are very particular to write rho Vy into Vx, similarly rho Vy into Vx leaving and then entering. Okay. Of course, at that point of time I did tell you that we will discuss this later, why are we so specific about the order of Vy when Vx. Of course, magnitude wise there is no change at all, Vx into Vy, Vy into Vx is same, but for understanding wise this way of ordering becomes very helpful for us. Okay. Okay, just an example to understand the convective momentum flux tensor, the components of the convective momentum flux tensor. Take an example which I discussed earlier. Okay. This we discussed when we discussed applications of differential mass balance. The geometry of this example is that you have 2 plates, you have closely spaced parallel plates, and then the bottom plate is porous, and you have air entering this, and it goes radially. That is what is shown here. It is a radial flow, but we analyze the problem in using Cartesian coordinates. So, you have 2 plates and flow entering in this direction and flowing in these 2 directions. Okay. And that is what is shown here. Quickly let us read. Air flows into the narrow gap of height h between closely spaced parallel plates through a porous surface as shown. In this example we used both the integral balance and the differential balance, mass balance. In fact, use a control volume with outer surface located at position x. So, this was our control volume. Okay. To show that the uniform velocity in the x direction is Vx equal to V naught x by h. So, we use the integral balance to find this, and that expression is given here. Then we use a differential balance, differential mass balance, find expression for the velocity component in the y direction. So, this was determined by using a differential mass balance. Till this point it is same as the earlier problem, only additional part which you have to find out is find the components of the convective momentum flux tensor. That alone is new. The geometry, description, the velocity components are all same as we have discussed earlier. Okay. So, now remember the reason for choosing the example is that example where we have both the velocity components, so that you can have better understanding of the, at least instead of 9 components we will have 4 components at least. Okay. Otherwise, we will end up in only 1 component and so on. Okay. So, and of course, Vx depends on x, Vy depends on y. Okay. So, now convective momentum flux tensor, we have seen this earlier. What I have shown here are only 4 components of the 9 components, because there are only 2 directions here. 2 directions for fluid flow and 2 directions for the momentum. Now, that as we have seen in the previous slides, the 4 components are rho Vx Vx, rho Vx Vy, rho Vy Vx and rho Vy Vy. Very simple. We are given the x component of velocity, we are given the y component of velocity, just simple substitution will give us these expressions for the momentum flux tensor. Okay. How do you interpret this? If you look at this control volume, just ignore the z direction, because we have only x and y axis here, variation along x and y direction here. Here we said rho Vx Vx represents, and then of course multiply by delta z represents the rate of flow of momentum entering and then leaving along x direction. Similarly, here rate of momentum entering and leaving along y direction. But those were because we had a control volume and one phase here, one phase here, we talked about entering and leaving. Now, we have reduced to a point and reduce this control volume to a small control volume, they have become a point. So, this rho Vx Vx represents of course we do not have area here, so it becomes flux, it represents momentum flux at a point. So, the way in which you should imagine is you have a small region and you have at every point there is inflow and outflow, and because these two phases have come together, there is no question of writing x and x plus delta x, they just become a point value, that is why we write as rho Vx into Vx. Okay. Now, along for the x component of the linear momentum balance, we have these two terms. Okay. Remember, the second component is Vx and the flow is both in the x direction and y direction, second component is along the x direction. So, what are the corresponding terms here? This term, of course, there is, we do not discuss about out and inflow, only at a particular point, and then these two. Okay. What we have discussed is rho Vx Vx and rho Vy Vx. If you write the y momentum balance, then these two terms will appear. Okay. So, this term and this term will appear in the x momentum balance. If you write the y momentum balance, then these two terms will appear, and they are because of mass flow in x direction, mass flow in the y direction. Okay. And of course, these expressions are simple to write, just simple multiplication. Okay. And that is what is shown here. We have just to show you where these terms appear in the linear momentum balance equation. Okay. So, we will write down the linear momentum balance equation and identify. So, what is shown here is the convective momentum flux tensor, and what is shown here are the components, the relevant components for this particular example. Only these 4 components are relevant to us, all others are not relevant to us. Okay. And what we have here is these two appear as these two terms here, of course, we are not differentiated. Okay. And these two terms rho Vx Vy, rho Vy Vy are, as I told you, appearing in the y momentum balance. Okay. So, give some idea of what are the components of the momentum flux, convective momentum flux tensor. Okay. This equation is just the z momentum balance, we are not considering that because it is a 2 dimensional example. Okay. Okay.